Dear friends, in the series of learning gas turbine technology, so we are analyzing the gas turbine performances. So in the previous video, we have seen about how the gas turbine engine works and how it is that the efficiency of the gas turbine cycle, it depends on the pressure ratio. Okay, so that even though it is we have derived based on the by using the turbine work and compressor work, and but finally we obtained efficiency. Okay, it's equal to 1 minus 1 by rp power gamma minus 1 by gamma. So from that we understood that that efficiency depends only on the pressure ratio, so and also the specific heat ratio. Okay, so but we will discuss more about the performance performance parameters. Because we need to understand certain things in the gas turbine analysis, especially how the specific work output is the function of pressure ratio and temperature ratio, and also how the efficiency varies with respect to the pressure ratio. So and those things we'll discuss. First let us see about the specific that means specific work output. So specific work output, that is we have derived the formula, that means we got the formula in the previous class itself. That is nothing but that means Wn by Cp T1, that is equal to T into 1 minus 1 by C minus C minus 1. Okay, so this is what we have seen in the previous. That means while deriving the efficiency formula, we got this expression. So this is what called specific work output. This one. This is nothing but specific work output. Okay. So now what we need to understand, how the specific work output is the function of T and C. Okay, from this formula we can see that specific work output is the function of T and C. Also particularly what we can say, this T, so it depends on the T, that T is nothing but we know that T is nothing but T3 by T1. So this we have seen. Okay, and C is nothing but Rp power gamma minus 1 by gamma. So this also we have seen in the, that means we have made this assumption, and we based on that only we got this formula. How this T is important? The T is important because here you see the T is depends on the maximum cycle temperature. This T depends on the that mainly depends on T3, maximum cycle temperature. So this maximum cycle temperature is very important in the case of specific work output. So because this temperature one, that is what we call it as, it is called a metallurgical limit. This is called metallurgical this is called a metallurgical limit. So it means this temperature that means should be assigned to the turbine blades. The turbine blades should withstand that highly stressed turbine blades should withstand this temperature. So that is one thing we have to understand. So that is why it is called a metallurgical limit. So if the turbine blades doesn't have the ability to withstand this temperature, then so that is how we are losing the performance. Okay, then this is one thing. Then next thing is this T varies for different. Okay, suppose T equal to this value, we say 3.5 to 4.5 for industrial gas turbine, industrial applications. So the gas turbine used in the industrial application, no? So for that, the T value should be around this. So T is nothing but this ratio, that means maximum temperature to the minimum temperature, we can say, that is the compressor entry temperature. So this ratio should be applicable for the industrial gas turbine. And then yeah, we can just say industrial gas turbine. Then this is this ratio is 5 to 5.5. If you have this ratio, it is for a aircraft gas turbine. So for the aircraft gas turbine, so this ratio is advisable. So that is what we we have to understand based on this specific work output. So now this specific work output also that means plays with the curve, that means with respect to the graph. For the fixed value of t, the specific work output, how it varies. Okay, so that we can plot it in the graph. So that is nothing but so we can just plot it. Yeah, so now let's plot the values. So it means yeah, this is the graph for the specific work output. So this is just we can say Wn by Cp T1. Then this is horizontal axis, nothing but Rp. So this is Rp. Okay, we can just say this is 5, 10, 15, then 20. So here also we can just say yeah, 0.5, then 1, then 1.5, then 2, like this. Okay, so now what happened particularly for the that Rp pressure ratio, when it is 1, then this curve something like this, it goes like this. So means it rises and then falls. Okay, so that is what we are obtaining when Rp equal to 1. So this value we can take it as Rp equal to 1. So for that we are getting this such kind of graph. Then when Rp equal to that means this is, so that means this is for t equal to, we can just say for the fixed value of t, that is t equal to 2, then this curve becomes like this. So then another curve, okay, it is for it is for t equal to 3. Then yeah, this is t equal to 4. Yes. Then we have this one. Okay, so this is t equal to 5. So okay, what this curve exhibits results is nothing but as we are going for the higher and higher t value for the fixed value of t, then the for the curve also becomes constant okay, as we go for higher t value. So when t equal to 5, this curve almost okay straight, that means it okay, it is constant. Okay, so constant for certain pressure ratio. So this curve is okay becoming constant for certain pressure ratio, and at this point the specific work output is maximum. So because at this point we can just say specific work output is maximum for certain pressure ratio. Okay, so that is what we have to understand. So specific work output becomes maximum for a given value of t at a certain pressure ratio. So this one thing okay we have to understand, and this curve becomes straight as we go for higher and higher. That means the curve becomes constant okay at the higher pressure ratio also we can say. So constant okay as we go for higher and higher value of t. So this is okay, this is one thing okay we have to understand from this graph. So also yeah, we can see that when Rp equal to 1, Rp equal to 1 means this is C. Okay, C, okay, in C only Rp comes. When Rp equal to 1, then what happened? When okay, so C becomes 1. That is the idea. So when C becomes 1, in this formula we can see when C becomes 1, so 1 by 1, okay, 1, so 1 minus 1 0, so then 1 minus, okay, again 1 minus 1 0, so this is also 0, this is also 0, finally your work output is 0. So that is what we have to understand. When RP equal to 1, specific work output is 0, so that is one thing, okay, we have to note down. And specific work output is 0, nothing but work output is 0, okay, so that is what so we have to note down. Then when RP equal to, okay, something, so just we can say as the pressure ratio. So this also, okay, we can note down, yeah, so that ratio, that graph we need to draw it, yes, let us draw this graph. We do have one more graph, so there is nothing but when yeah, this is R, that is nothing but this is efficiency, this is RP. So here also, okay, the starting point we can just say 1, so RP 1 and RP 5, 10, 15 and 20, okay, so like this. So when RP equal to 1, when RP equal to 1, so how this, okay, this curve becomes something like this, it is like this, so the curve is like this. So this is for gamma equal to 1.4, and we do have a one more curve, so that is nothing but for gamma equal to 1.67. so this is for gamma equal to 1.4, and it is for gamma equal to 1.67. okay, so that means your efficiency is higher, so we can just say this, okay, for the monoatomic gases. So monoatomic gases, when R equal to 1.67, then your efficiency is higher than R equal to 1.4. So that is what here we are understanding. As the RP increases, your efficiency also increases, and after, okay, reaching certain level, then the efficiency, okay, becomes almost, okay, becomes constant. So this curve, okay, will be keep going only. So after certain pressure ratio, this efficiency will be okay, will be a constant. So that is what here we have to understand. And another thing is we are going to see about this one. That means at a different pressure ratio, how it is. Okay, because one thing is for a constant, that means pressure ratio, that means at RP equal to 1, and also RP equal to this pressure ratio, the RP equal to 1, then also RP equal to, see this one, we just say now this is T power gamma by gamma minus 1. So how we obtain this, okay, we will just discuss with the another graph. So yeah, I think this specific work output graph is clear, and also this efficiency graph. So yeah, we have seen that efficiency is 0 when RP equal to 1, efficiency is 0. So that also we can understand from the formula. So because very simple is it, okay, so because efficiency equal to yeah, efficiency equal to, we know 1 minus 1 by RP power gamma minus 1 by gamma. So when RP is 1, okay, so and here this is efficiency becoming 0. So that is what we have shown it in the efficiency versus pressure ratio curve. So this is one thing. Then when this pressure ratio occurs, when this condition occurs, so what is going to happen? Okay, so that is what we have to see. So this is the curve. This is the curve. So yeah, okay, this is a TS curve. So we all know, okay, for the normal gas turbine cycle, the TS cycle, okay, so TS cycle is something like this. TS curve is something like this. Yeah, so this is 1 and 2 and 3 and 4. Okay, so this is let's say this is, yeah. Okay, so now yeah, this is nothing but TS curve. Okay, we all know. So okay, how this TS curve, from this TS curve we are going to understand certain factor. So first thing is, when we say RP equal to 1, when we say RP equal to 1, it means our P2 by P1 is becoming 1. That is what we have to understand, because RP generally we say RP equal to P2 by P1. So this is equal to okay, when this is equal to 1, it means we say indirectly we say P2 equal to P1. So when P2 will become equal to P1, that means when these two curves, because here only P2 okay equal to constant, yeah, and here P1 equal to constant. So when these two curves coincide, so that is what we say, when this curve becomes okay something very closer, so like this, yeah, so when this okay this curve sinks to this condition, then this is also okay reaching this condition. That is what here we have to understand, this curve reaching this condition, because yeah, so when this condition is, yeah, when this condition is achieved, okay, so when we say RP equal to 1, it means here only we say it is. So when you say RP equal to 1, this is what okay RP equal to 1. So when this okay condition occurs, say you are both okay, so this condition when we say this is achieved, then we indirectly we are saying W equal to 0, okay, because that is what we have seen from the previous curve, that is our specific work output curve. So when RP equal to 1, that our work done is 0. So that is all, that is what okay this the curve shrinking, or okay shrinking and extending in this direction, this curve represents. So here RP equal to 1, and then okay we say that your W is 0. And in another way, what happened when RP equal to T power this, when this condition achieved, so it means okay the curve is extending, okay extending in this direction. So the curve is okay gets shrink and extending in this direction. So yeah, so this is what, so when RP okay, that means when RP equal to T power R okay R by R minus 1, so then what happened, our curve becomes like this. It means both the this is compression process and this is expansion process, both the compression process and the expansion process coincides. So that is what here we have to understand, when RP equal to T, this one, this condition, so that time our compression process and expansion process coincides. If this happens, then what happened, so this is what we say, here it is nothing but T3, this is nothing but T3, and this point is nothing but T1. So T3 okay T1, so T3 by T1, that is what RP, this T. So your RP is now equal to T3 by T1. So that is what our T also, this one, whole power gamma minus 1 by yeah gamma by gamma minus 1. Okay, so when this condition is achieved, so that time also your work is 0. This is what we have to understand. So when this condition achieved, work is 0. It means your turbine work okay equal to compressor work. When this condition okay, here when we are having this condition, then also your network output is 0, network is 0. So because here both the process coincides, compressor work okay that means compression process and turbine process coincides. So when this condition occurs, your work also will be 0. So in this condition, so we are getting this one, RP equal to T3 by T1. So suppose okay, if this is a condition okay we are achieving, then yeah, here also we can just say Yeah, this one in this graph. Here also work is 0 and here also work is 0. Okay, so this is what we have to understand. Okay, when rp equal to 1, when rp equal to t power r by r minus 1, what happens? Okay, how this that means our performance of the gas turbine cycle differs. Okay, or how we are achieving the work done, that is equal to 0. So that is what we have to understand